All right. Well, it's 7:05. We will start our meeting tonight. Thank you for coming. Thank you for making your way today. It's not cold or snowy or icy, so it was great weather to come and meet tonight. Let's start with prayer. So, dear Lord, thank you for allowing us to meet. Thank you for the wonders that you've shown us through your creation. Thank you for this world, this galaxy, this universe in which we are able to look at you and wonder everything that you have done, about everything you've done. Lord, we pray that you show us new things today about your love and about your wonderful creation tonight. Thank you for bringing Steve here, and that's it.
Okay.
Well, this one is our last in the apologetics meeting for the year. We will be skipping December. We will be meeting back again on the third Thursday of January. And tonight we have our very own Steve Baertschi with this fascinating presentation. For those who are online and don't know Steve, Steve is a chemist, he's a pharmaceutical scientist, and of course, a committed Christian. Steve has a PhD in organic chemistry from Vanderbilt University. He was named a fellow of the American Association of Pharmaceutical Scientists. He has published more than 90 scientific articles and book chapters, including 2 editions of a book on drug degradation. He retired from Eli Lilly and Company after 26 years. He is now an independent consultant focusing on the pharmaceutical industry. Steve has a wife, his wife Cheryl, 4 boys who I don't know yet, and 2 grandchildren. He is active in his local church and Bible study fellowship, and he's one of the scholars in the scholar community for Reasons to Believe. So, Steve, thank you for doing this for us.
All right. I don't know where you got all that information, but you did some sleuthing, I think, on your own.
I had a little help.
So I originally gave a presentation pretty close to what I'm going to give tonight at Reasons to Believe headquarters when I was a visiting scholar a year and a half ago. They make you make up some topics and give some presentations, and so they kind of pushed me on this, and I'm glad they did, because I discovered and learned some good, interesting things. And I'm not an astronomer or a physicist, and I'm going to be dabbling in some of that. So forgive me for some of my naivety, but I'll try to keep it somewhat light and focused on the essential points, which will hopefully be intuitively obvious to the casual observer. Now, if my mouse will work, there we go. So we do have a few people here. We have a few people online. So this should remind us of something. Now, what show does this remind you of? Star Wars, a long time ago in a galaxy far, far away. So we know that from Star Wars. And what's the other one out there, the big show besides Star Wars? Star Trek. Okay, so you've got some of the characters here, and you've got this little who knows what this little green guy his name is? Is it Baby Yoda, or
Played on TV.
I'm not getting that very far.
it's Grogu. So that's from The Mandalorian. That's another Star Wars spinoff. But we know from Star Wars and also from Star Trek that there's a lot of other civilizations throughout the universe, and most of them, if not many, if not most, precede us, right? So we're relatively new to the scene. We know that from science fiction. So in this particular scene in Star Trek, this weird looking creature there with a dress that's sort of androgynous looking, there was a series where it's sort of a panspermia theme, where this ancient civilization billions of years ago was really sophisticated, and they planted their seeds across the universe in sort of a pattern, actually. And they were waiting until their offspring were get to the, and they've died out long since, and they were waiting for their offspring to come to a certain place where then they would be smart enough to accept and learn about their ancestors. And this is a hologram here of this guy coming to tell them, you are all part of you all have heritage with us, you are from us, get along together, love one another, sort of thing. So it's an interesting reinforcement of the common scientific thing that and science fiction people that just generally out there that believe that there's universe, there's people, there's civilizations, there's intelligent beings all throughout the universe. So what drives the belief, the speculation that we are not the first or we're not alone? So if you just look out in space and think about, remember the Hubble telescope, and then there was the deep Hubble, the ultra deep Hubble, where if you held a dime at the distance of your arm and looked at the eye of Roosevelt, that's the amount of space they mapped with deep Hubble and then ultra deep Hubble. And they found in that they went from 3,000 to 10,000 lights or stars, and then they zoned in on that and they found out there was really 10,000 galaxies that they uncovered, and that may not be the total number, but you multiply that in three-dimensionally all around you, and you start to think of the vastness of the number of galaxies, and it's mind-boggling. So you look out there in space. Once it's reported that Billy Graham looked at his wife Ruth looking out at the stars and said, "You think there's life out there?" And she said, "Well, Billy, if there's not, it sure does seem like a tremendous waste of space." So that's what most people would think, that it's either a great waste of space because it's so vast. There's, and we think about
Can't read that, okay.
I can't
um,
at all.
the vastness of space. There's the number of stars are estimated to be from 10 to the 22 to 10 to the 24 stars. And that's a large number that's hard for people to get around their minds around. So as a chemist, I want to think of comparing that to Avogadro's number. So if you have 12 grams of carbon, you have Avogadro's number of atoms, or 6.022 times 10 to the 23rd. So roughly, if you think about that number in 12 grams of carbon, it's the same number of atoms in that amount as there are stars in the universe, roughly, because roughly it's 0.167 moles to 1.67 moles of stars. So as a chemist, I think it's really just a mole. There's a mole of stars out there. And if you take the entire weight of the universe, then you know what the, you can know the proton count and you can know the atomic weight of the universe, 1 mole. That doesn't mean anything to you, but some of the chemists out there, it'll mean something too. So let's hone in on just one of the trillions of galaxies, the Milky Way itself, our galaxy, our local galaxy. And here's obviously it's not a picture, it's a rendition of an artist's imagination of scientifically driven of where our sun is in the Milky Way and the size of the Milky Way, which is roughly 100,000, at least in this dimension, the way I'm showing it, 100,000 light years, 100,000 light years across. So it's very large. And if you think about Star Trek trying to get across, even at warp 9, where they're going almost the speed of light, it still takes a long time. So they couldn't have ever left the galaxy. They could only work in a little part of the galaxy. And so it's a little bit naive to think about exploring different galaxies and ever getting there, right? Because it's such a large, vast universe with so much space in between. Well, with so many stars and so much time, there's a lot of people that think that life must be inevitable. And why do they think that? One reason is because they find us here. So they know if you don't believe in a God and you don't believe any design, you believe that it's all chance and natural, it has to be possible, right? Because it happened at least once. And necessitists will kind of, there are two camps, the necessitists and contingentists. Necessitists believe that life is inevitable, and we're one example of that inevitability. And therefore, in a universe so vast, there's got to be other places like this, or even different enough that different kinds of life form could form. So it's not improbable, it's inevitable. It's just a matter of time. Contingentists think that life is a highly contingent event that depends on a conspiracy of highly improbable conditions. Life is improbable and might not have been attained any other planet or any other place in the universe. So you've got people think it's obviously definitely going to happen eventually, and it has happened once. And those that think it's, boy, we look like we're in a Goldilocks region of how did it ever come about? So as a chemist, I want to think about what are some of the things needed for life from a chemistry point of view. And first thing I think about is the periodic table. What elements are needed? Now, physicists would think about this too, and astronomers, but as a chemist, it's one thing I can at least start to grasp. So you really, the purple, this is the periodic table with colored. So the purple squares are the elements that are absolutely required for life as best we know it in a carbon-based world. And the green ones are speculated that they're probably also needed for life and definitely needed for human life. So in order to have life, you have to have a relatively high amount of all of these elements. They don't have to be the same amount, but there's got to be a fair amount. And the problem is, and hold on a second, I gotta go. The problem is we are constrained to carbon-based chemistry. And let's think about this for a second. We know that all life is based around carbon because carbon is a tetravalent element. It allows a great complexity of structures to be formed and utilized in the life processes. And here's an example. If you look at the upper left-hand side, you've got the DNA, and you see the interesting shapes and how it has to get unwound and wound back up and read and transcribed. On the upper right hand, you see some beautiful protein structures from nucleic acids, not nucleic acids, from amino acids that can form really complex structures to be the molecular machines that we need to be alive. And another example here is a molecular motor of the flagellum. I believe that's part of a flagellum molecular motor, but it's very simple, yet it's very elegant and beautiful. And here's a little movie going on. I hope you can see that of a kinase walking. It's a kinase enzyme or a protein walking along a microtubule in a cell, pulling its load. And this is an animation of what really happens with kinases and how they work to transport loads, things physically within a cell. And it's difficult to imagine other kinds of chemistry that are not carbon-based that could do that. So is life constrained to carbon-based chemistry? Absolutely. And that's pretty much the consensus. You'll see science fiction kind of movies that talk about other chemistries and other exotic life forms, and they go to silicon because silicon is in the same family as carbon, and so it has some of the same characteristics of its bonding capabilities, and you can imagine complex structures being made. And that's about the only one that you can imagine could potentially work. So they always go to silicon. But silicon is just completely not viable because respiratory cycles will not work with it because of the bonding of silicon. If you have respiration going on, it's going to go to silicon dioxide, which is highly insoluble, soluble, instead of carbon dioxide, which is volatile. So it works with carbon. It does not work with silicon. So we are stuck with the elements in the periodic table, and we are stuck with carbon. So we can't just magically believe in some other life forms that don't correspond to these elements. But we've got to get carbon. So if we go back to the Big Bang, and we're going to talk naturalistically here about how the universe formed, how long ago, and what atoms were formed when, what elements were formed when. The Big Bang, about 13.8 billion years ago, and after about 20 minutes and for tens of millions of years, the only elements we had were hydrogen nuclei, helium nuclei, a little bit of deuterium, a little bit of helium, and a smidgen of lithium. So you've got no possibility of life occurring for a long time after the Big Bang. what you had next, and I'm not an astronomer and I won't try to explain something I don't know very well, but first generation stars began to form as soon as 100 million, maybe even sooner than that after the Big Bang. And this led to the creation of more elements because as the hydrogen and helium come together and it gets a large enough planet, or whatever you want to call it, a star, it gets compressed enough to start to form what's the word? So fusion happens in the core, and it starts to create other elements. And over time, that wears itself out, and then it goes supernova and spews out stardust into the universe, which is got more elements that are not just hydrogen and helium. And you're starting to make larger molecular weight. And that's one generation. Then you have another generation forming maybe as soon as 100 million years after the that's first generation. So that gives you a few of the extra elements that you need. But the consensus seems to be that you really need at least 2 generations of stars to form enough of the carbon, nitrogen, oxygen, and other elements that we showed a little bit earlier to have life even begin to have a possibility. And you probably need to have some neutron stars form, which are just highly condensed, just neutrons, just completely super heavy, collide with each other, and then they spew out most of the other heavier elements. There may be other ways to get to the heavier elements, but they speculate, or they think that neutron star mergers are a big part of how the heavier metals were formed, and that takes a while. So it's a certain amount of time before you even have the elements possible for life. So most people that I'm reading and understand believe it's third generation. You need a third generation star, which our sun is a third generation star. It is highly metallic. That is, it has not just hydrogen and helium, but it has our oxygen, carbon, nitrogen, silicon, and it's making more of that as it goes on. It also, you need thorium, you need radioactivity for your planet. You need thorium-232 and uranium-238. And so that's something that probably only happens with neutron star mergers or some exotic events. So that kind of radioactive decay, internal eating, you form planets, and the planets need to have radioactive decay to have a molten center. And you see, I could spend a lot of time on this, and I'm going to really just skim over this, but a molten center that gives you a gravitational field, it gives you a protective field against so that we can see the aurora borealis like we've been seeing recently, that the magnetic field that protects us from the molten iron in the center. So that kind of internal heating and the plate tectonics and protective magnetic field all provide enough stability to give you the chance of having habitability. Some, if not most, of the astronomers out there that I've been reading, I can't see on this because of where it's at, they speculate, they seem to think that our Earth is in a Goldilocks region. It's a Goldilocks location, it's a Goldilocks concentration of radiogenic elements, and it's habitable only because it's a special privileged planet. And I won't talk about this plate tectonics in detail, but other than to say the plate tectonics drive renewal of the surface of the Earth that has allowed it to transform from an inorganic, lifeless surface to something that could support life and the production of organic materials that could eventually be utilized to form life. So if we go through the time frame of how to get to that point where you can have a planet that exists in a habitable zone, has plate tectonics and a magnetosphere protection, you think about at least 2 generations of stars, and you go through the timeline here. Let me see if I have this. The timeline here from the Big Bang on the left, from 13.8 billion years ago to about the time we believe the Earth was formed, about 4.6 billion years ago. Third generation star. You can see on the top it says at least 2 generations of stars with the elements CHNOSP and water needed to sustain life, along with thorium and uranium. That let's look at I'm going to skip this just for a second. The life on Earth starting after the Earth formed some length of time. So habitability in the universe, this famous Carl Sagan wannabe Neil deGrasse Tyson, I got to switch my location, has been caught saying, or he has said this actually, the universe is a deadly place. At every opportunity, it's trying to kill us. And the reality is, if you get outside of Earth, it's very inhospitable to life everywhere we look. And so it is a little bit like we get this special little privileged planet here that's protected and stable and habitable. And it's a bit of a problem for those who think that life is inevitable and that life came about naturally. Astronomers see an accumulation of evidence that the Earth resides in a rare, likely unique cosmic safe zone. One more indication of cosmic providence. This was a quote from Hugh Ross in this article here. And if you want to study more about how much design and preparation there is in the Earth where we live and in the place of the universe, Designed to the Core is a very good book for that, for exploring that topic in more detail. But let's look at how much time between the formation of the Earth and the arrival and habitability and arrival of life on Earth. So there was a what they call the late heavy bombardment about 4.1 to 3.8 billion years ago. And if you look at this little graph, you'll see that red line where it shows the frequency of impacts, like asteroids impacting on the Earth. And you see that time frame there is about 4 billion years ago when we had a lot of bombardment when the Earth was very young. And then we had another late bombardment that was very intense. And they call it the Hadean era, where the energy on the Earth, it was so hot that we're a liquid, we're a molten surface, no liquid water, no solid rocks could have survived. So there's no way you could have life on that, and you couldn't have any fossils from that either, because
Fossil record.
they were molten, right? But if you look at when life is believed to have begun, right about the consensus is about 3.8 billion years ago, and that the green line on the left shows when that happened after the late heavy bombardment. It's like there's a minimal amount of time after that late heavy bombardment when the Earth cooled that all of a sudden life arises. There's not a lot of time for chemical evolution and abiogenesis to take place. Almost looks like a minimalistic time. And if you look at when the first fossils began, the fossils that we have uncovered go back to about, do I have that, 3.5 billion years ago. So it's we're starting right after the Earth is cool enough to even consider having a prebiotic soup. And that amount of time from the late heavy bombardment to life's origin is estimated to be between 10 and 100 million years, which is just a drop in the ocean. It's a very short period of cosmic time. And it's difficult to imagine that being enough time from a naturalistic point of view. I'll editorialize here. So the literature says, this one is just in 2021 here, there seems to be a real puzzle in need of explanation. Why have we humans appeared so early in the history of the universe? So not only early in the history of the Earth, but early in the history of the universe. There's an article that I pulled out from 2016 from actually it's a Harvard and Oxford collaboration. And the guy from Harvard that wrote this is the same guy who's getting publicized right now for being the one that thinks this comet coming towards us could be an alien spacecraft. But he is. So I looked at I was a little worried, is this guy a nutcase? So I looked at the references, the citations since 2016. There was about 80 of them, and none of them contradicted what he's saying here. There's pretty much a consensus of what is being said here. And so I'll go through what's being said. What is the relative probability for the emergence of life as a function of cosmic time? And so here's the criteria: star formation history and stellar mass function. So that means we got to have stars and a certain type of star. The lifetime of stars as a function of their mass. So you've got to have stars around for a certain length of time. the probability of an Earth mass planet in the habitable zone, because if you get too big, the gravity's too high, it's too intense. If it's too small, there's a lot of problems. So we're kind of in that Goldilocks region. And life as we know it, according to the standard cosmological model, which is lambda CDM, or cold dark matter, or what is popularly called Big Bang, essentially, and assumption of essentially no time between habitability and formation of life. So they're really stacking the deck in their favor to make it possible to have life. And here's the results. When they did a lot of calculations in probability, and they said the probability of us existing now is at 0.1% at most, which means anywhere else in the universe, doesn't matter about how far away it is, anywhere else in the universe now is about as soon as you could expect life to have a place to be habitable, to exist. So at least 99.9% chance that we exist at the earliest possible time point in cosmic history. So, to me, suggesting something of a bit of somebody's what's that Fred Hoyle quote? Somebody's fiddled with the universe on their own. Somebody very smart. So probability disclaimers is they even admit in this article
with the dials.
Ken. So it's a lot worse than projected, actually, in this article, and they list out the things that would make it worse. So first, they say the estimate is based on the minimalistic set of assumptions. So they had to do that in order to make it fit that we're even alive now, right? That there's any probability. The more refined models would push that probability out into the future. Basically, they're saying it's so unlikely to have occurred this quickly that it's more likely to happen in the future. And the fact that they assume that life would happen immediately after the planet becomes habitable, which, like, that doesn't even leave time for the monkeys typing on a typewriter to do some nice novels, right, in infinity. So more refined estimates, and they call out these more refined estimates in the paper. Here's a few of the things that they call out: the existence of a moon to give a stabilized climate, the existence of asteroid belts that we have in our solar system, because that's needed. And I won't go into why, but that's one of the requirements. You need to have a stable habitable zone. The orbital structure of the host planetary system, the effects of a binary star companion, the location of the planetary system in the galaxy type and location. So these are just a few more that each one of those would take that likelihood down from 0.1% to 0.01 to 0.01 and it starts to get, it's even worse than that. It's much worse than that, actually. Hugh Ross has created a page where he tracks from the literature the parameters that they believe are required for life, a life support body. And they've identified 322 of them. And the probability for occurrence of all 322 parameters are approximately 10 to the minus 304 power, which is, you can't even fathom 1 in 10 to the 304th power. And if you think about the maximum possible number of life support bodies, which are planets, well, we said there are a number of stars were 10 to 22 to 10 to the 24. And Andrew has let me know that roughly the best estimates he could find are about 2 to 3 planets per star is the best estimate, probably more towards the 2 range. So it's a pretty good number. So you just assume every star could have a habitable. It's 10 to the 22, and so if you do a little math there, that's less than 1 chance in 10 to 282 to the 282nd power that life exists. That another even one such life supporting body would occur anywhere in the universe without invoking divine miracles. So, from a purely naturalistic point of view, there's a problem with just coming up with another place that's habitable like the Earth based on what you pull out of the literature. I'm not talking about based on what you pull out of the Bible or something else. So the reality is, little Grogu, Yoda, they don't exist, at least not yet. And if they do exist anywhere in the universe, it would be now, and it would have been created by God, because there's no way to get there from a naturalistic probability point of view. So my conclusions, there's just a couple more pages of slides, and then we'll go to Q&A and challenges or discussion. In spite of the vastness of our universe and the unbelievable, it's incomprehensible almost, and the significant age, which you can debate about that a little bit, but just from a cosmic time point of view, the consensus appears to be that 3.8 billion years is apparently the minimum time needed to prepare the universe for a life in one spot. Therefore, from a naturalistic point of view, our civilization is likely first with a much, much greater than 99.9% probability. Remember the 10 to the 282 or whatever I said, it's much more probable than that. That our civilization is the first. And so some would, you know, I want to say that God isn't slow. He doesn't waste time. And I'll bring this back around to life arrived in the minimum time needed at just the right time, because God was preparing the universe for us to exist. And he's now gone, as he's told us in the Bible, that he's gone on to prepare another place. He's preparing the new heavens and new earth. And this from John 14, Jesus said, "My Father's house has many rooms. If that were not so, would I have told you that I'm going to prepare a place for you? And if I go and prepare a place for you, I will come back and take you to be with me, so that you also may be where I am." So all this preparation that went on in our universe may be going on similarly, or maybe even more lavishly in a new universe that we will be introduced to, where there's a new heaven and a new earth. And think about this also, that God is not slow, right? Because with the Lord, 1,000 years is and 1,000 days are like 1,000 years are like 1 day, right? So with the Lord, as 1,000 years and 1,000 years as 1 day. But God isn't slow. He's not slow in keeping his promise, as some of you understand slowness. He is patient, not wanting anyone to perish, but everyone to come to repentance. So he isn't slow, he's patient. And so I think we should think about that, and let's use our time well as we every day go about always being prepared to give a defense to anyone who asks us the reason for the hope that is in us. That let's use our time well, let's not waste our time, and let's always be prepared. And that's all I got to say about that.
Thank you, Steve. I'm ready for the question and answer session. I think you can increase the volume now on your computer.
All right, now can you see who might be asking, if anybody's asking questions online?
I don't see anybody, so
Okay, we got one from here in the room from Andrew, a professor from Ball State of physics,
But not a chemist.
but not a
So I
chemist.
got chemistry questions for you.
Okay,
You had up there your periodic table of the elements of the elements that you were highlighting, saying these are the ones minimum necessary for life. Could you expand on that and tell us more about, you know, what we absolutely have to have, and then what we use also? Maybe we don't absolutely have to have it, but we do use it.
okay, so I'm going to kind of repeat that. So I'm being asked to talk a little bit more about what elements we actually use and why we need them, for what purpose, and which ones are there that are needed, and how we use them as well.
Yeah, and because you know, as you mentioned, the three populations of stars and the fusion furnaces that make them, I wonder about, you know, when did we have the complete set available?
Yeah,
and
and
what is the complete set?
So he's asking, what is the complete set of the relative amounts of all the different elements that are needed for life, and when were they available as a function of time? And you could have a whole course on that, actually. And as I went through that online, from a function of time, you're going to have localized bursts of certain kinds of elements, and it's got to take a lot of mixing and evolution of time. Best I could tell, they think it's about, because you need a third generation star, is about 13+ billion years to get there. There are some references that I found out there that suggest that you could have localized areas in much shorter period of time so that maybe there is a possibility of, but I don't see that in the generalized consensus view of astronomers and physicists. But I can't defend it one way or the other. I'll say this from the molecular machines that run our bodies have to, they're made up of carbon, nitrogen, oxygen, sulfur, phosphorus, and a few other things. Those things are absolute minimum because the main structures are in DNA. It's got all those amino acids, and many of the proteins have transition metals such as iron, manganese. Somebody help me. Tin that are then bound into the protein, and without it, they're not active. So there's a whole lot of transition metals that are used by proteins to create certain shapes and activities because they create redox potentials across certain locations of a protein. So you can't do it without also some transition metals, and without, it's too laborious to go through this, and all of the examples, but there's numerous examples. And I think though that periodic table I showed you captures it's probably a minimalistic set as well, because you find selenium and arsenic and all kinds of things are kind of needed at real trace levels in order for functioning. But you could argue that they're maybe not needed for all life forms and in levels. So the consensus that I find is about 13 to 13.8 billion, about 9 billion years ago. About 5 billion years ago is when we started to have enough of the elements, probably. And then they had to congeal around a star and planet formation. And so that's the next step that took a few billion years. So maybe 8 to 9 to 10 billion years is probably when you had enough of all of the elements to start looking at the possibility of creating life.
So your periodic table which you had up there with the highlights, that's like the minimum set. But then there's probably, there's more that we use beyond that minimum.
I'm going to go back to that just to kind of, so he's asking, there's probably, how complete is this set? This set right here with the purple and green is probably a pretty good minimalistic set for humans and for advanced forms of life, not for all bacteria and viruses and whatnot. And does my biochemistry friends agree with that? We seem to have consensus in this room with a very small number.
Ken has a question online.
Ken Wogemuth?
Yeah.
Yeah.
I
I agree with you. That's probably pretty much a minimum.
Okay, good.
Yeah.
And if you want to talk to somebody about radioisotopic dating and not just radioisotopic, but all kinds of dating, Ken Wogemuth, who just spoke, gives a great talk on dating methods beyond just radiometric dating.
He's
Right,
the
Ken?
expert.
Right, Ken? You're a go-to expert.
Yeah, I do one like that. And I'm not sure if I have another one that I've gotten just about the last year, in that I focus on the minimum of geology and geochemistry necessity for life. So I take what you've just done, and then I get a little more focus. I develop the plate tectonics a little bit more, but then I also include water is very, very significant. And the composition of the atmosphere is incredibly unique. Now, I'd have to go back and look at every talk I gave the last 2 years that I've given it to this chapter, and that's what I can't remember off the top of my head.
Yeah, but you're giving us some ideas for a follow-up topic next year.
Bringing you up.
Oh yeah, that's fine. I'm still here. I'm still alive and kicking.
All right.
I will make one comment. You were correct that the origins of life are about 2.7 billion ago from the Earth, 2.7 or to 2.8 or maybe 3 billion years. Yeah. And then that's when the fossils, we began to see fossils. Now, that's correct specifically but also for somebody not too familiar with the whole story, when they think of fossil beds, they think more of the ones that have shells and trilobites and things like that. The ones, the early 2.8 to about 600 million years ago were only small single-celled, organisms, algae, various kinds of algae and cyanobacteria, not shells that we see as physical fossils when we use the phrase a fossil find. So just
And is that discovered by looking at the composition? How is that known to be fossil?
they can see the evidence, yeah, that these are cyanobacteria. But I'm just making the point that when we, in a general audience, as we all are, when we say a fossil bed, we're thinking of the trilobites and the shells and the corals. Those didn't come until multi-cell organisms could begin to grow at about 600 million years ago, because the oxygen level was so low.
So that would be after the great oxygenation event. But can you see the slide I have up right now?
Yeah.
You keep saying 2.5, and I want you to check
Oh,
my
no.
numbers here. It's
Oh, I'm
3.5.
sorry. Oh, I'd agree with you. Let's see.
Fossils extend back, or the fossil
Ice origin
evidence
3.8. I'm sorry. Yeah.
Yeah. Okay.
And 3.5. Yeah, I'm okay. I'm sorry. I used 2. I
Yeah.
should have just read your, if I looked over and looked at it. Thank you for saying that.
Yeah, good. I was afraid I was
Oh.
off a billion years, which is a
No,
lot.
no, not at all. But these are cyanobacteria. They can be observed, but then you're looking at sort of ancient rocks that are solid and it's bacteria. It's not organisms that crawl around. Is my only point.
Yeah, gotcha.
So that's
Okay. We've got a question here in the room.
Yeah.
More of a comment, I guess, is, as time has gone on from a while back, this problem has only gotten worse from a probabilistic standpoint.
Yeah.
I
So
remember back, I remember giving a talk on this when I was in 7th grade of all things. The old Drake equation that Frank Drake put together for the probability of this was intelligent life in the universe, and they had all these factors, multiply them together, and you see there's gazillions of them. And it was so ignorant in terms of what they knew about what it really took just to have life at all,
yeah.
let alone something that's sophisticated.
Right. So what was just said in the room, if you can't hear it, is basically the Drake equation, which is really kind of what I'm building on, is the number of parameters needed to create life in the universe somewhere. And the Drake equation sort of calculates that based on number of stars, number of planets, this, that, and the other. It's gotten, every few years goes by, and instead of us getting closer to the probability being more like, yeah, there's got to be life outside of Earth, it gets worse and worse, because there's more and more parameters that are discovered that appear to be critical for life to exist. So the Drake equation has gotten much longer, more variables, and the probability has gone down more and more and more every few years, every year, you could say. Was there another question online?
Yeah, I've got one, Steve. Can you hear me?
Yes, Bill Current.
Yeah. Well, just a couple of comments first. When the Earth formed, you had essentially an ocean covering the Earth, and water covered the surface of the Earth, and it said, and God was brooding over the surface. This is in Genesis. And you think about that and you look at the history of the Earth, what happens is sulfur-reducing bacteria. They didn't need oxygen. Sulfur was their oxygen that they used to drive their metabolism. And the heavy elements were so abundant and in solution in the water that it took maybe 1 million years for the sulfur-reducing bacteria to deposit for example, iron and the other minerals that are essentially poisonous at certain levels. And you look at all of the other elements that are essential poisons that need to be in existence at very small amounts. You think about the fine tuning that was involved in that and the organisms that were involved, depositing uh, the heavy metals
Yeah.
and
And-
burying those in the earth and then leaving behind just the right amount to support life.
Yeah, and that's where plate tectonics comes in very important, because things get
Yes.
subducted and then refreshed, and you've got the silicon oxide and silicates, and there's a whole cycles that the geologists know more about than you and I, Bill, but we've read a little bit about it, right? But wait, it just occurred to me as you were talking about the where the Bible starts in terms of where it says water covered the surface of the earth, it would appear then, if you look at that life's origin line, that it's just to the left of that. It would be after the earth cooled down enough to allow replenishment of the water through, comets, presumably coming to earth and bringing the water. And I don't know, I haven't read anything on it. I'm just thinking out loud. Is that in anybody's experience what we think?
Yeah.
When
I
when it
think
was a
so.
water world would be right after the Hadean era, right?
Yeah. But no, it would be, yeah, just right after the Hadean. So it's between that and say the Cambrian explosion, all of that was going on that Ken was talking about. But the interesting thing is the fine tuning that was involved in getting all of the heavy metals buried and having the right amount of heavy metals available for life. And then you look at, I think that part of the history of the earth has been ignored when people are looking for life somewhere out there. They're always chasing water.
Yeah.
But if you find big bodies of water that occurred just after the third generation stars that had gone supernova, they're completely full of heavy metals that would kill any life. So you have to go through a period of having unicellular organisms that can metabolize that and deposit it in the bottom of the oceans. So
And
chasing
so
water, I don't think is a good strategy for finding life. Water is probably the most abundant, one of the most abundant molecules in the universe.
yeah, what I see from it is the way the hand of God is involved in preparing and formulating the world to be inhabitable. And as we look out, we see this to be a unique. Now some people, there's no biblical reason to think that we're unique, that there aren't other places. It doesn't bother me at all to think that there may be life forms elsewhere. But the more we learn scientifically and naturalistically from the science, it appears that gets more and more highly unlikely. And so then I see it as maybe seeing evidences of God's hand at work to prepare a place for us. And then I think about what he's doing now, because he's going to prepare another place where with new heaven and a new earth. And so gives us something to look forward to, because it's going to be much better.
And I've learned things, just like you were saying, Steve, over the last 5 years. I've become convinced that God just is involved in sustaining everything all the time. Is about where I come out now.
Well, that doesn't sound too heretical to me. We had another comment in the room here.
So speaking to your point that the aliens are improbable,
Yeah.
I think Dr. Loeb is too rosy in his estimation. I think the real number is much, much worse than that.
And and this is Dr. Loeb is the physicist or the astrophysicist at Harvard, who has he wants to find a naturalistic way for life to exist or life to create. And so he's done some work which he says shows that many more stars and many more planets will form many millions and billions of years in the future. And that runs counter to many lines of thought which say that things are becoming more diffuse, entropy is going down. It's not going to work that way, but I don't have to deal with that. But that's kind of what you're saying, isn't it?
Well, I don't agree with the 0.1% number as a probability. I think that the probability of life, the probability that we would exist naturalistically, is so crushed into the noise that there's just no way we should be here. And I don't think there's any other aliens. And to that point, then, if aliens appear, who are they? I think it's if aliens appear on CNN tomorrow, okay, to me, there's basically two choices. Either they're fake government aliens that are, like about the same thing as the UFOs from, Mojave, California.
Roswell, yeah.
Or they're extra dimensional beings.
Yeah.
I think those are actually in the biblical worldview and in a cynical, conservative political worldview. I think those are actually more probable than actual aliens from another planet.
What's the term then? Transdimensional or supernatural?
Yeah, so you're either getting demons or you're getting some, CIA Star Wars to cover up, whatever.
Yeah.
And that's what I'm gonna think when I see the alien.
And this idea that you're expressing is consistent with the Hugh Ross and who's the other author? I can't remember. Mark Clark of Little Green Men and what's the full title?
I don't remember.
There's but basically he says biblically think. What is it called?
Lights in the Sky.
Lights in the Sky and Little Green Men, where he basically says these things that we're seeing UFOs defy the laws of physics many times, and so it's not possible that a living form. These must be transdimensional, which and it explores the occult, the closeness to the occult in the sightings of these things, and suggests that that these must be demonic, either angelic or demonic, spirit beings that we're seeing, which would be consistent with biblical worldview, or they wouldn't be inconsistent with a biblical worldview. And we're not going to talk about cosmic time in Gerald Schroeder's paradigm that I know you would love to talk about afterward.
Any other comment or any other question?
Separate from what you already presented, but from a chemist's perspective, do you have thoughts on the requirements of the early chemical environment to produce the biomolecules that we see today in stable form that could be used to somehow, we'll just say magically, come together to form life?
So the question is there, as a chemist, can I see any path that chemical evolution could create the building blocks of life in such a way that they could stay around long enough to combine and have any chance of forming the superstructures needed for life? And I think I would echo what James Tour says on this, and that is time is your enemy, not your friend. In other words, most naturalistic people say, well, given enough time. And I think the problem with that is that I studied drug degradation in my career, main part of my career, and molecules that are interesting from a biological point of view are almost invariably quite unstable. And so time is your enemy in that they don't stay around long enough. So you'd have to have some way of creating them and then creating a pool that maintains extreme stability until then they're needed and put in the right situation physically to be able to kind of aggregate and form. And I haven't seen any even remotely plausible explanations for that. And James Tour has done a nice 13-part series to discuss this in somewhat nauseating but exciting detail for a chemist online. So they're about hour-long videos, about 13 of them, and he goes in detail through some of the thinking that I'm just touching upon. But I think as a degradation chemist, if you call me, time is not your friend, time is your enemy. You need things to happen fast when you have these highly unstable molecules, or you'd have to build them up. And they're trying to solve this, but they're not making good progress because every time they make one discovery, the fence post is moved a little further apart, and it's oftentimes related to stability and the ways, the complications needed to get things assembled. So no, I think is the short answer to your question.
Any other question?
Any questions online?
Let me make, you know,
One more from the room.
comment is, you look at the size of the universe, complexity of the universe. That's there, and it's made to produce us. And us for God's glory. Just the extravagant power and wisdom and glory that's represented in this universe, and doing all that just so we can be here, so that he can redeem us.
Yeah,
It's
it's mind-boggling. And some people, the skeptic will say, what a tremendous waste. What a tremendous, how inefficient could you possibly be? And the believer looks at it and says, what a lavish, loving God that he would do all this just to create one spot. That said, I think there's nothing biblically or theologically that says that God couldn't have created other living beings in other parts of the universe that we know nothing about. That does not threaten my faith at all, because I see no exclusion from that biblically in it, but it just doesn't seem naturalistically possible. So I think the one is extreme waste, right? What a waste of space. How terribly inefficient could a God be? Or how much God loves us that he would lavish and demonstrate his majesty through something so crazy.
Just speaking to that comment, if there were some being, 10 billion light years from now, the difficulty of encountering that being also suggests that, at least to us, it's as if they're not there. If they do show up, they would have some kind of space warp, which is some sort of extra dimensional travel. Because if you just got in the car and hit the gas, and cranked it up to 50% of the speed of light, well, I mean, as you point out, the whole galaxy is 100,000 light years across, right? So it's going to take them way too long to show up.
Yeah.
So if they were to show up, they're almost certainly extra dimensional beings or bad fakes by the government. Probably. One other question. You mentioned silicon. And I know, I tell people when they ask about this, well, I know the chemists put a lot of effort into this and tried it a lot, and they sort of concluded that, you're not going to do it. Could you speak a bit more into the chemistry of silicon as a life molecule and as not working as a life molecule, sort of what was done on that?
Okay, so could I speak any more? This is so people make sure that online they heard. Could I speak any more to the implausibility of silicon as a life molecule, that where life forms could be silicon based and not carbon based? First thing I'll do is cite Fazali Rana, who authored a book, and the name of the book escapes me right now, but he talks about this in some detail with references, and that's what I went through and looked at the references and kind of convinced myself, yeah, this is right. But the simple aspect of it is you need electron transport for energy purposes in respiration purposes for living forms. In carbon, it works perfectly because carbon gets oxidized to CO2, which then is volatile and can be removed from the living form, and then utilized by another form to create oxygen and material, right? Organic material. So that's the photosynthesis and the respiration cycle. It all kind of makes sense because something can be removed. In a silicon-based life scenario, they haven't been able to come up with a way where respiration can occur such that oxidation of silicon or respiration of silicon doesn't result in something that's insoluble and then gets stuck in the living being. So it falls apart immediately as soon as they start scratching the surface of looking at, could this work? What's attractive about it is that silicon is tetrahedral and that it can bond 4 four things around it, like carbon can. And so it's like, oh, that gives you the possibility of having complicated structures, but the stability and the insolubility problems, there's some stability problems with silicon bonds, and with silicon oxygen, it loves oxygen, so it keeps going to oxygen. And so you would have a hard time exchanging it for carbon because it's not as,
So basically you were exhaling sand.
yeah, the sand is
That's-
the easiest one, but it's not as what's it called when oh my goodness, when people sleep around with other people, what's that called?
Promiscuous.
Promiscuous. It's not promiscuous enough to bond to so many things well, like carbon can bond to so many different things well in different ways, that it provides such a wealth of structures that can be formed, that you can see how it forms these molecular machines that can carry out life, and it can carry out respiration and everything else. So it just is the perfect molecule to be element to be base of life off of. They can't find any other trying. They've tried, they've kind of given up, I think. And their SETI, search for extraterrestrial life, they pretty much know you can't get away from water, and you can't get away from carbon in terms of life. So, but I'm not doing a very good course long job on, but I can't give you that reference. It's a book that then
It's a
references
book.
the literature to what's that?
Creating life in the lab.
Creating Life in the Lab by Fuzzerana. And then he talks about the problems that they've had in creating life in the lab. And one of those is, can you go to other non-carbon based life forms? Anything else? Anybody else online want to make a comment or chime in?
Well, thank you, Steve, for the talk. And,
All right.
Thank you so much.
Thank you very much.
Thanks, Ken.
We're going to put this in the YouTube Reasons to Believe Indianapolis, because I don't know if we can rename it, but anyways, it'll be there
Yeah.
for you to see or to share if you need to. So thank you, everybody, and we'll see you then in January. And Ken, we have you in our site.
Okay, that's fine. Nope, I still enjoy doing this.
Thank you, Ken. Good night to everybody.
Thanks, Steve.
All right. Thank you.